Hi there, in this video we're going to have another look at the complex exponential and see how it relates to the Fourier series. Okay, now in a previous video we derived this equation here, that e to the I theta equals cos theta plus I sin theta. Now we think about this here as a phasor rotating in a complex plane. Okay, so this would be the imaginary axis and this would be the real axis. So that's the real part of e to the I theta, which is the cos theta, and this is the imaginary part of e to the I theta, which is the sin theta. And this phasor is rotating in the anti-clockwise direction, and that's the angle there that we've got, theta. Now you have to be careful, and as I mentioned in a previous video, this is different from saying that you've got some function y and some function x on the real number line. So that's a real number line, that's a real number line, and that's an angle theta, and that's the cos of the angle theta, and that's the sine of the angle theta, and it's rotating, say, in that direction there. Now it looks like the same thing, but it's different. It's fundamentally different. This is a mapping from the real number line onto the real number line. This here is a mapping from the real number line onto the complex plane. Okay, and it does it via e to the I theta, okay, via complex exponential. So although they look similar, they in effect they're different things. Okay, so just to keep that in mind. Now we're going to introduce the idea of angular frequency, which is radians per second. So let's imagine this thing here, this phasor is rotating round in the anti-clockwise direction. So we know that one full revolution is 2 pi radians. Okay, so if this was going at 5 hertz, which is 5 revolutions per second, so every second this would go round 5 times. So the question is, how far would it have gone in angular terms? Well, it would have gone round once, which is 2 pi, and then it would have gone round another once, which would be 4 pi, all the way round. So when it goes round 5 times, it would have gone round 5 times 2 pi, it would have gone round 10 pi radians. Okay, so let's say it's gone round 10 pi radians, okay, in 1 second. So let's give it 5 seconds. So we'll wait for 5 seconds. So in 5 seconds it would have went round, well, it would have round 10 pi radians in the first second, okay, and the second second it would have round 20 pi radians all the way along to the 5th second. So in the 5th second it went round 5 times 5 times 2 pi, and went round 50 pi radians. Okay, so we could write that out as 2 pi f t. Okay, so it's going round 2 pi times the frequency, the number of times a second it goes round, times the number of seconds that you've actually waited. Okay, so then we can replace the idea of this theta here, which is the angle, with a value of omega t. Okay, so that's 2 pi ft. So it's saying the same thing, okay, but it's just writing it out in a different format, and you're introducing an independent variable here of t. Okay, so let's have a wee look further down here. So now if I was to draw that out and I drew the t-axis, okay, so now we've got a three-dimensional drawing here, and that would be the t-axis there. Now that there is the real part, and that's the imaginary part, and it's travelling in an anti-clockwise direction. If you were to spread this out along the t-axis, then you would form a corkscrew. You can see it's appearing there. Okay, now how tight the screw is and how wide it is would always depend on the frequency. Okay, so a high frequency would be a very, very tight corkscrew, and a low frequency would be a very, very wide corkscrew. Now if you were able to look in from, say, this angle here, so you're looking in this direction, then you could see that you wouldn't be looking at the real axis because it's the flattened plane here. So we're coming down here and we're looking through, and we're going to be looking in this plane here, so it's the imaginary and that's the time. So if we looked in that plane there, then what we would see would be the imaginary part, so that's imaginary, that's time, which would be the sine omega t, and then equally, if you were to come from above and look down on this, then you wouldn't be looking at the imaginary part, you'd be looking at the real part with respect to time. So you'd be looking at this plane here, okay, so that's that plane there, okay, which is it's perpendicular to this plane, the original plane we were looking at, and we would see the real part. So the real part here would be your cos value here, okay, so that's what we would see. Now what we're going to do is I'll have a wee look at that actually. In fact, I can bring it up now, so let's have a look. There we go. I have to actually bring up my MATLAB there so as I can bring it on. Okay, so that's what we're looking at here. And so again, we've got the imaginary axis here, okay, and we've got the real axis. So the real axis in effect runs up here, okay, and that's the time axis there. Okay, so there we have our corkscrew there, and there we have, if we look in for that angle there, we have our sine, okay, and then from that angle there we have our, looking at the real axis is our cosine. So let me see if I can just get this into the same kind of format. As you see this here, now what I'll do is I'll actually turn it, and if I go to this plane here, which would be the imaginary plane, so we're expecting to see, in the imaginary plane, expecting to see the sine, okay. So if I switch this round, I'll actually go all the way around like that. Let's see, so there we coming. So that's us coming in here, yep, okay, and trying to get it, there we go. So we're actually looking in from the, if I go back to the drawing here, let's see, so we're actually looking in, so we're looking in from this angle here, okay, can you see this actually? There we go. We're looking in from this angle here, okay, and we're expecting to see our sine wave there, okay, and that's just exactly what we're seeing. Let's see, go back in there and MATLAB. Okay, so that's exactly what we're seeing. We're looking in, we're seeing our sine wave. Okay, now I can just bring it back round. Okay, so there we go. Again, that's us. That's us looking there. So that was our looking at our sine. Now, if we were to go in and look directly from above, okay, well, we would expect to see our cosine. So we come in here and we look at it, try to get it so you can see it changing directly from above. So that's, we're coming round and we'll spin it right round. That's us looking directly from above, and we will get our cosine. Okay, it just runs down that way because I would have to turn it round 180 degrees, wouldn't I, in order to get it like that. So there we go. That's us looking in right from above, and that's us getting our cosine there. Okay, so that gives a good indication. Obviously you can look in directly from this end here all the way through, and all you'll see is just your circle. Okay, so we come in here and all you've got is your real axis and your imaginary axis. Okay, so that gives a good indication. I mean, I suppose a picture paints 1,000 words. Okay, so that's your complex exponential done in 3D, and you can see the cosine part and the sine part. Okay, so let's go back to our smooth draw and we'll come back in and finish this off. Let's see. Okay, so that's us looked at our corkscrew. Now if we were to look at e to the minus I omega t, well, that would be cos of minus omega t and I sine of minus omega t. Now the cosine function there, if you were to draw the cosine function out, if you went in cos of minus theta, okay, would equal cos of theta, which is the same height there, okay, and because sine is an odd function, we would have the cos of the sine of minus theta equals minus the sine of theta. Okay, so then if you put that in, you would end up with e to I omega t minus I omega t will equal cos omega t minus I sine omega t, and that would in effect produce a corkscrew which would just rotate in the opposite direction. Okay, now Another thing to note is that when we're doing our Fourier series, we're not dealing with a continuous frequency omega. We're dealing with a, a, a fundamental frequency omega naught. So, for example, 5 um, 5 hertz, and we're going to be taking integer multiples of it, so n equals 1 up to some value. Okay, so let's just say n equals 1 to infinity. So it would be, if it was 5 hertz was the fundamental frequency, the next one would be 10. Okay, and the next one would be 3 times that would be 15, 20. It would continue on like that. Okay, so we could write this complex exponential, which it was written originally e to the I theta. We could write that as e to the I. Well, we've replaced the theta by our omega naught t. Okay, now we're replacing it by n omega naught t because it's just integer multiples of that omega naught t. So we could write that as cos n omega naught t plus I sine n omega naught t. Okay, now if we go back to our original derivation, this was our original derivation of the Fourier series. Okay, so that's just as what we've seen in the previous video. Okay, now another thing to note here is that the reason for introducing that, because you look at that and you say, well, why bother? Why bother introducing all this complexity into this? Why don't you just keep it simple and just don't bother with it? Well, the problem is that this here, the Fourier series here, it's in the context it's in at the moment, it's only able to approximate functions of period 2 pi, because the functions that you're using for approximations are the cosine and the sine, and these have got periods of 2 pi, so it means that you would only ever be able to approximate in this form functions of that period. Okay, so let's say we had another function that came along, say it was a square wave like that, and that function there, it didn't have a period of 2 pi, so let's say 2 pi is over here, so there's your sine. Okay, and you've got that, and there's your sine there, and it finishes here. Okay, it doesn't have a period of 2 pi, it has a period of 10 pi. Okay, so that's going to hit a point there of 0, and we don't want to hit a point of 0 there. Okay, we want our 0 point, say, to be over here. So what in effect we have to do is we have to scale the axes in order to fit into that period. Okay, so let's say that I have a period of 10 pi, then what we would have to do is we'd have to scale that axis back to 2 pi, but we can scale that by multiplying by 2 pi upon that period there. Okay, the period of 10. Okay, so it would be 2 pi upon 10 times 10, which we get back to a value of 2 pi. So, or if we write it more generally, we'd be scaling it by a value of 2 pi upon L, okay, where L is the period of that function that you're trying to approximate. So we could then replace this here, this value here, nx, with n, and now x would now be 2 pi upon Lx. Okay, so this process here of multiplying by 2 pi upon L is what we use in order to scale it, in order to ensure that we can approximate functions of any period L. Now, just to finish off, what we do in electrical engineering is that we would take this e to the I n omega naught t, and we would write it as cos n omega naught t plus I sin n omega naught t, which is equivalent to, we just open this out, would be cos n 2 pi f t plus I sin n 2 pi f t. Now that is equivalent to cos n 2 pi. Now the frequency of the function is just 1 over a period. The period is t naught. So then we can write that as cos n 2 pi upon t naught t plus I sin n 2 pi t naught up 2 pi upon t naught t. Now again, the reason for doing that is that this 2 pi upon t naught is a scaling factor. Okay, so it's exactly the same as we've got here. Okay, but we're just writing it in terms of our period to t naught and in terms of electrical engineering, okay, or signal processing. So L there is just the t naught there. Okay, so just finishing off, I've just written out then the Fourier series in terms of these new values. So we would have f of t equals a0, the sum for any one at infinity an cos n omega naught t, okay, and bn sin n omega naught t, and we would have, originally it would be a 1 upon 2 pi would have been what we'd have used to find the a0. Now the 2 pi is just the period, okay, so we can just then replace that by 1 upon the period, which is t naught, and also the limits of integration go over a full period minus pi to pi. Now the period now is t naught, so we can just go from 0 to t naught. You could of course go from t upon 2, t naught upon 2 to minus t naught upon 2, and you can do that if it makes the mathematics easier. And again the an would be replaced, because it's 1 upon pi, that would have to be replaced by 2 upon t naught, because in effect it would be 1 upon t naught upon 2, which is the same as 2 upon t naught. Okay, and the same thing goes for the bn there. Okay, you'd end up with 2 upon t naught. Okay, so that's all I have to say. It was just a video to add in a few extras, okay, to see where some of these other additions come from. Okay, so thanks for listening and goodbye.